Welcome back to the program. In this, the final section, we will explain how it is possible to control a process which has a non-linear response. pH has a non-linear response. To grasp this, let's first explain pH. pH is simply how acid or how alkali a substance is. Acidity is the exact opposite to alkalinity, and these conditions are defined on a pH scale ranging from 1 to 14. For example, a substance with a pH of 1 is said to be very acidic, whereas a substance with a pH of 13 is termed very alkali. A substance with a pH of 7 is neither acid nor alkali and is said to be neutral. One last very important point to mention here is that pH values do not follow an ordinary number scale. For example, a substance with a pH of 2 is not twice as alkali as a substance with a pH of 1. In fact, it is 10 times as alkali as the substance with a pH of 1. And a substance with a pH of 7 is 1,000,000 times as alkali as a substance with a pH of 1. This renders the pH scale non-linear, which is the purpose of our last advanced process controller, the adaptive controller. We return to the plant where the feed-forward system has been running as planned for the last 2 days. Today is the 3rd day. The product is spoilt and the plant is at a standstill. Let's explain. For the first 2 days, the pH of component B varied between 6,3 and 6,6. Acid was added as programmed and the pH remained at the desired value. But on the 3rd day, the pH varied between 6,6 and 6,8. Even more acid was added than on the previous days, and there appeared to be nothing wrong with the process. Tests later revealed that the pH of component B was off specification, causing the product to be rejected. Here's what happened. The feed-forward controller had worked well based on the flow rate and pH of the component B. But on the 3rd day, the concentration of the acid additive varied considerably. And since there was no control system to monitor the pH after the feed-forward system had adjusted it, the pH remained high. You may recall that we mentioned this limitation when discussing the feed-forward controller. We mentioned earlier that adjusting or neutralizing pH is not a linear process. Let's use this graph to explain. A linear response means that the relationship between two variables is a constant and is represented by a straight line. Consider the two variables, speed and distance. The higher the speed, the greater the distance traveled. The plot of speed against distance produces a straight line. Speed and distance are said to have a linear relationship. This graph shows the relationship between pH and the quantity of acid required to lower the pH. The relationship between the two variables is nonlinear, as shown by the shape of the curve. Furthermore, the graph shows that a much greater quantity of acid is required to reduce the pH from 6,8 to 6,7 than is required to reduce the pH from 6,4 to 6,3. In summary, it was the nonlinear or logarithmic response of the pH and the lack of a suitable feedback loop that caused the system to fail. What was needed was a feedback control system with a nonlinear response to correct for the variances in the pH of the acid additive. The modification involved an additional pH sensor located downstream from the mixer tank and an additional acid supply line. Here's how it works. Based on flow and pH, the feed-forward controller adds the right amount of acid to component B to bring the variable pH to the desired level. Should the pH be incorrect after feed-forward action has been applied, the downstream sensor and adaptive controller forming the new feedback loop will detect the pH error and add additional acid to compensate. Let's summarize the important points of adaptive control. In the chemical plant, feed-forward control maintained the pH at the desired value most of the time. Feedback control was added to correct any further deviation in pH. Variations in acid concentration and the non-linear response of the pH required the use of an adaptive controller in the feedback loop, which automatically adjusted its response when the error was not corrected at the current settings. It was the ideal control element for the non-linear process of pH control. To conclude this module, let's briefly review the 4 types of advanced process control the chemical company used to ensure plant safety, product quality, and operating efficiency. From the basic PID controller, we introduced ratio control, where the input from one stream was used to adjust the flow in another stream, thereby maintaining a constant ratio between the 2 streams. Cascade control, where 2 feedback loops, one within the other, are used to minimize temperature variations. Feed-forward control. Disturbances in pH are measured and adjusted before they have a chance to affect the process. Adaptive control. The controller adjusts itself automatically to compensate for non-linearities in the process. We trust that you have enjoyed finding out about advanced control systems, and we look forward to having you participate in further Tech AV programs on the subject of automatic process control systems.